This is the Amp Hour Podcast, released December 15th, 2019. Episode 471. An interview with Matt Berggren. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Matt Berggren from Autodesk, run the Fusion 360 team.
All right. Welcome, Matt. How you doing?
Good. How are you?
Good. We are former coworkers.
We are. It feels weird introducing myself that way. I feel like I should just say, I'm Chris's friend Matt.
Right. So we worked together at Supply Frame doing some product stuff there.
Yep.
But you very obviously have a lot of EDA experience. And we'll talk a little bit about your background, but you are here to talk about I need a little bit of actually coaching on what the new title is. So it's Fusion 360, but also you were part of the Eagle transition, right?
So I was actually part of the Eagle acquisition. So I coordinated the Eagle acquisition for Autodesk. I came in not as a part of Eagle, but actually to coordinate the acquisition. And really the emphasis now is on electronics design in Fusion. So I would hesitate, we did borrow quite a bit from the Eagle technology that we acquired, but what we've done in the Fusion environment is new, novel. There's aspects of what looks like classical Eagle kind of in there, but that's more a familiarity thing. And there are still quite a bit more than that. So Fusion has this history of integrating lots and lots of technology in it. So an example would be something like HSM Works, which is used for like CNC machining, milling, cutting, that sort of thing. And when HSM, and I shouldn't say HSM Works, that's the SolidWorks implementation of it, but when HSM was integrated into Fusion, we dropped the HSM moniker. And that's in large part because, it's Fusion. Right. If we were trying to hide the strategy of what we're doing with Fusion, we could probably have picked a better name, like Diffusion or something like that. Fission.
You just call it Smush. You could have Smush.
Exactly. So, it was interesting though, because when we did the acquisition, I remember on EEV blog, other than being kind of taken apart for, oh my God, it's going to subscription. We hate you for going to subscription, blah, 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 blah. And that was later. That wasn't right at the point of the acquisition. A good friend from a university out in Pennsylvania had shot me a message over EV blog and said, I think what they're doing is integrating electronics design into Fusion 360. And if they do that, that's interesting. Curiously enough, he just shot me a message over Twitter the other day. And he said, hey, it looks like you guys are integrating electronics design in Fusion 360.
And actually, so give us some timelines on this. So when was the actual acquisition? And then
and I remember this distinctly for what's probably a tragic reason. So the timeline was we did the actual acquisition, closed the acquisition the day after the Brexit vote, which meant that, we had taken a bunch of USD, bought a bunch of pounds, and then the following day, of course, the pound sunk, right? So probably could have saved a little bit of money.
I was wondering why that was relevant, but that's what you're saying.
Nobody can predict those things, right? Those are macro forces that nobody can predict. But
what is the actual date? I don't know the date of Brexit.
June 2016. So I joined Autodesk in January. You can imagine it was a fairly steep ramp up to both land the acquisition, the same time try to do a lot of kind of portfolio rationalization. Because when I came in the door, we had Circuits.io, we had 123D, we had Tinkercad, all of those rolled up into me. So, trying to find a place for each of those things that didn't just sever the ties with each of their respective user bases was critical. And so then likewise, doing the Eagle acquisition, getting that in-house, and then you can imagine I've got a room full of people who are working on Circuits.io. How do I how do I break the news to that group that, hey, we went off and acquired this electronics design technology? But I think what we've landed, both with the combination of stuff that we did with Library IO and then the stuff that we've done with the Eagle acquisition and the integration with Fusion, kind of is the best of all of those worlds.
Yeah, and remind people what Circuits IO is.
Okay, so Circuits IO was electronics design in the browser. And, wherever you kind of fall on either side of that, probably the best example, best sort of analogy for people, if you just want to kind of orient yourself, is somewhere between fritzing and Upverter. Because it does have a breadboard editor. It does have, at the time, it had schematic capture and PCB layout, though pretty limited. But it was really the circuit simulator underneath that was the really exciting piece. So that's actually on Tinkercad today. So I also run the Tinkercad team, and shout out to my Tinkercad team. Tinkercad is mechanical design in the browser, designed for sort of, what we kind of euphemistically call like K to gray, which is a lot of pushing and pulling pixels and add, subtract, right? So I take a geometry, 3D geometry, whatever it is, a cylinder, a circle, or a sphere, a cube, I put them together, I add and subtract from one another, and I can build these reasonably sophisticated models without the same complexity that you might find in something like Fusion 360, right?
No generative design, no
generative design. Well, it's, it's
throwing stuff to server clusters and stuff like that. Right?
Exactly. Well, it's actually interesting though, because it's all of those kind of 3D modelers in the cloud are largely based on WebGL, 3JS, these sorts of things.
Oh, sure. Yeah.
And the distinction between mesh modeling and surface solids is lost on most people until you kind of get into that space and you have to hack your way through something like, hey, is this an edge?
Yeah. How do I mush these things together? Smush.
Yeah. Exactly. How do I've got a bunch of triangles.
Now, Matt, I will license you that name. I actually excellent. When you were speaking before, I registered the domain.
Excellent.
Autodesk Smush.
Of course, it's smush.sk. I couldn't get the premium version, but
that's right.
It's smush.tv.
That's right.
Yeah, so
no, that's quite different.
But the circuit simulator that's on Tinkercad is actually really interesting because it does instruction set simulation of the ATmega. So if you think about that in terms of integrating that with Spice, you have the analog simulation capability of Spice, but then if you have the instruction timing for the individual instructions, it actually kind of doesn't matter at that level what code you write on top of it. Whether you're running an RTOS or you're using Arduino drivers and services, doesn't really matter because you've captured the instruction timing. So, rising edge, falling edge timing, those sorts of things. And then you've got the individual instructions themselves and their sort of execution. When you put that in line with Spice simulation, it creates a whole bunch of really interesting kind of things that you can do with it. So that exists on the Tinkercad front. You can go there, write code actually for a virtualized Arduino, and other ATmega variants. There's even an ESP on the site, which is kind of interesting because you can have a device running in the browser and write code for the ESP8266, and that virtualized device can actually talk over Wi-Fi to an actual ESP8266.
Oh, wow.
So it's pretty interesting. It's a pretty interesting kind of conceptual model. But you can imagine if you're a teacher with a classroom of 30 kids, handing out a bunch of Arduinos and jumper wire and all of these other things, you hope to push that as far down the pipe as possible.
Right.
Because just putting it away at the end of the class period is going to take you the last 20 minutes.
Yeah, it's a material nightmare more than the actual content. Yeah. I do remember the box of even just dead 555s and 74 series logic, or even worse, the quote unquote working box when someone has zapped 3 out of every 10 chips in the box.
Exactly. So kids that are rubbing balloons against their heads and then stepping into electronics class, right?
Where'd you get that balloon? Where did it even come from?
why did you bring it in here for
We're
God's
using
sake?
chips from the 70s, man. There's no protection here.
Oh man. So then that capability is something that I'm actually really excited about.
Yeah, that sounds cool. And that's still under active development.
So that's still under active development. That exists on Tinkercad. So we introduced something it's a little over a year ago, called Tinkercad Circuits. And the eventual goal being that at some point a kid wants to put LEDs in the eyes of a dinosaur that they design and run wire through three-dimensional space. We should be able to draw sort of conduit paths, for lack of a better term, for the wire to run through the body of the dinosaur, and then they can throw it onto a 3D printer, run the LEDs into it. And we have a few examples of that actually up on the website, which are things that are sort of plug and play. You can stick, this unit into that body, do the subtract, and it will put an LED inside of something.
Oh, yeah. Yeah. So like just like a standard 5mm or something like that.
Correct. Yeah. So standard 5mm LED, but also with like the coin cell in it. So 3D printable, nice kind of unit with a switch on the bottom or something like that. So you can put a coin cell in it, 5mm LED will shine off of it, and then you subtract the whole unit from the body of the three-dimensional object.
Yeah.
And that has been really interesting. The uptake on that is huge. And every time that we show it to teachers going to something like ISTE, which is a big educators conference, their response is, oh my God, where have you been all my life? And how do I teach this?
Yeah.
But so that capability from Circuits.io was really the differentiated feature that persists today. And I think my ultimate goal would be to continue to extend that technology so that on one side you would have what exists in Tinkercad as sort of bootstrapping the market itself, right? Because there's market forces at work here. I don't want to shy away from that and say that we're a commercial business, because I think there's too many people that do that. We don't need one more in me.
It's an interesting thing too, though. Like you said with teachers, I mean, you have kids who are designing electronics into stuff they're 3D printing. 3D printing is just such a part of education these days, and like in making. And then then you're going to have kids that are growing up, even 4, 5, 6 years later, they're just like, well, wait, I can't put electronics in my designs. I think that leads very naturally into, maybe I will, take a look at something like Fusion. Maybe we'll
introduce this other piece into the curriculum. Yeah. And so Tinkercad, it's interesting. Tinkercad has this export to Fusion, and just right at the intersection, the interplay of how do you make a mesh modeler talk to a solid modeler.
Yeah.
So, if you've ever played around in any of the sort of mechanical modeling tools, when you bounce in there and then you go, to some website somewhere, you grab, STL or some other, OBJ, something that's been meshed. You bring it into those tools and you're like, oh my gosh, I can't do anything with it.
Right.
We address that in a somewhat unique way. Now, Fusion has a mesh to what we call BREP conversion. So BREP is boundary representation. That's the solid modeling kind of standard form.
Yeah.
And then the mesh conversion on that is really much more sophisticated. But on the Tinkercad side, we had tried to build a segue from mesh modeling, which is, the OBJ3JS kind of representation of data. And it turns out that the easy way to do that is to actually not store the model, but store the recipe. So if somebody draws a body and it's a cube, and we know that cube is volumetrically 3 by 3 by 3, whatever the units are, irrespective of units. If you store the recipe for how they got there, I did a sketch. The sketch looked like this. I extruded that sketch by this.
Right.
You can play back that recipe, and it's not rocket science. It's actually parametric modeling, but it's parametric modeling expressed in a somewhat different way, where what we're storing in terms of parametric data is actually stored sort of behind the scenes, so that kids don't have to see a timeline and scrub forward and backward and make changes to legacy stuff and then play it back out to see how that changes things. Totally has its place in the professional world, but if you tried to introduce parametric modeling to kids too early, it would be a little bit crazy. But we did a few other kind of interesting things there. Added Scratch for parametric modeling so that somebody can actually build a sort of procedural model and say, okay, do this, do this, do this, do this, and now make that. Now let me go back and change the variable values and see what else it does. So all that's kind of on the Tinkercad side, but there is a bridge from Tinkercad into Fusion that allows somebody to start there. I think the inevitability of taking the circuit simulation capability that we have both in Tinkercad and in Eagle today and extending that to have more capability, more interactivity. It's the natural sort of bleed into what I would kind of, hopefully characterize as like circuit analysis 2.0, right? Yeah. Like, I think we've got to get past the 741 op amp. I mean, I think that's a great example, but I think there's more interactivity, and looking at what my son has done in the program at Santa Cruz, where he is, the software that they use, it still looks old and feels old, and it feels like, you look at it connecting wires and digital logic diagrams and things like that, and you think, gosh, like this could be so much better. And I mean, you'll probably recall when I was teaching all the workshops in San Francisco, I did a lot of that, kind of pro bono. We can talk about that at some point. But I remember distinctly one time saying to a crowd of people in a workshop that
these are Eagle workshops, we should say.
Yeah, exactly. So teaching people how to use Eagle for electronics design, and very practical stuff. How do you solder a BGA, right? Well, it turns out it's actually not that hard. It's probably one of the easier components to solder if you know how to screen solder paste, because you've got so much surface tension, you've got a decent stencil. It's like set it and forget it, right? Shove it in the oven and everything's good. But doing those workshops, I remember saying to a class of people, like, gosh, if they just gave me Eagle for like 6 months, I would rock this thing. And that's in large part because of the history, right? Like coming from Axel EDA and then later Protel and then Altium. And I've got this long kind of sordid history in EDA. It was really fortuitous that all this stuff kind of came to a head when it did. And I got my comeuppance, I guess.
Yeah. Let's go back, actually. Let's go back to where you got started first and then work our way through EDA. So how'd you get started in electronics in the first place? I mean, you're on the software side of electronics now, but you were, a long-time hardware person.
Yeah, absolutely. So I got started in electronics, like so many people. We always quip that there's only two ways that you get into electronics, right? Ham radio or electric guitar. And
I think that the common one here is taking things apart, but I think that's true in both of those hobbies as well.
Yeah, exactly. Yeah. And I think those, both of those hobbies are things that can be meaningfully improved by taking something apart. And especially with electric guitar, improvement is not always improvement. It's a little bit more subjective. If I want to overdrive this thing, I can absolutely do some horrible stuff to it. But no, so it was some combination of that. It was right at the intersection of that. So, I grew up in a house with a ham radio dad, grew up around radio most of my life. Lots of very interesting manually strung dipole antennas across the house. Nice. Don't touch both ends of that, that sort of thing. And even today, I go back to my parents' house. There's a dipole stretched across my bedroom from corner to corner. But the early days of that were really around the guys who were essential kind of contributors to the early days of Zenith, if you remember that. So my dad, my uncle, a number of other folks were all from Zenith, right? So
Zenith, like the television maker?
Yeah, Zenith, like the television maker. So at some point, that was a very progressive company, right? Zenith, Curtis Mathis. I mean, remember those names? Like you have to be really old to remember Curtis Mathis.
I'm sure some listeners out there are, but Zenith is basically, Zenith to me is like, oh, that's like the thing I could have pulled out of the trash because it was something, an old enough TV that someone was upgrading it. But at the time, it was a great TV.
Well, and they were pioneers in things like the early remote control. So, original IR remote controls came out of their R&D lab.
Cool. Okay.
Wired remote controls, things like that. So they had a lot of quality of life improvements that they were making to the TV, competing against companies like RCA. right?
Yeah.
So, so I grew up in a household with, a dad that was an engineer, uncles that were engineers, surrounded by lots of ham radio equipment, and kind of progressed through that. Eventually hit high school. Rebellion was guitar. The joke's on me because, playing guitar didn't mean that I didn't learn more about engineering.
That's
My
right.
dad
Yeah.
could smirk and sit on the recliner and watch me toil away trying to get overdrive
Just like,
out of
oh
something.
no,
and say,
not rock and roll with all that loud electronics.
That's right. Where's the solder? So I kind of progressed up through that, and then eventually really just committed myself to the hardware side of things in a big way. Came up through the .com period. Worked at Microwave Communications Incorporated. I saw that you, for whatever reason, were reading a microwave book. You're gonna have to tell me about that. But Microwave Communications Incorporated, if people don't know, that was MCI. So
wait, MCI, not like the phone company?
Yeah, like the phone company. That's what
no
it was.
way! I didn't know that.
MCI was Microwave Communications Incorporated. So the original company was bootstrapped, building microwave transceivers that would communicate between Chicago and St. Louis.
Got it. Okay.
Don't ask why St. Louis, right? I don't know. Maybe the arches. I don't. Yeah.
But it's really flat to get there. I guess you probably
pretty much line of sight, right? Just can you just lift the pole another 2 feet?
Curvature of the Earth. Yeah, you just gotta get real tall poles and you're fine. Yeah.
So gravitational influence on the energy moving in that direction will arc it along the contours of the. Yeah. Anyway, so that was kind of what launched me into the .com period. And, MCI was acquired by WorldCom. WorldCom famously was one of the big players in the early .com period, led by a guy who very controversially ended up, driving the company into bankruptcy. But he was the guy that broke up the bells. That was Bernie Ebbers.
Yeah. Okay.
And he was the one that kind of opened up all of the telco infrastructure that was largely government funded, but managed by, at that time, I think AT&T, and had kind of was one of the key players in the early .com by simply by virtue of giving everybody equal access to the telecommunications networks, so that you can't plug into this network without making it available to people commercially. So, or you can't build out this network or build on this network without making the aspects of that you contribute to it something, I will very much be reluctant to say like an open source project, because I don't think anybody was really excited about building other people's infrastructure. But if you think about it, a lot of that infrastructure was in fact, built by multiple companies, all contributing to the same back end.
Right. And really, as the consumer, kind of a greater good in terms of just built more resources to be used, even if people didn't really know what they were getting in that process.
Yeah, exactly. So, and that kind of landed me out in California. The .com out in California famously imploded, and then it was as you were kind of watching the world fall apart. I had been using schematic and PCB tools for a long time. Knew some guys that had a product called PCAD through a company called Excel EDA. Used to be Excel version 14 and 15 and blah 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 blah. And took a job in EDA. And I got the job. Actually, it's interesting. I got the job as a technical consultant. It was a weird role. They were doing this road show where they were going to go city to city and talk about high-speed design and microwave circuits and RF circuits and things like that, and all these things that you could do in PCAD. And like many EDA companies, and this is probably not well understood, like many EDA companies, the people that are really customer facing don't necessarily have a background. This it kind of contributes to the imposter syndrome in engineering, but it's that there's a very famous quip from Kevin Morris, who writes FPGA Journal, that says that, engineers are in constant fear of being found out. Yeah. You put somebody who has been supporting customers building electronics for 20 years out on the road, and you say, okay, now, we want to do a high-speed design workshop, you kind of need to find somebody who knows something about that stuff. So I kind of came in under that, and then XLEDA was very quickly acquired by then Protel.
Okay. So you were out doing the road shows and doing like demos and
so
customer facing stuff.
So a lot of customer facing stuff, and you develop through that process a real sense of both customer empathy, but then kind of self-awareness from a software engineering standpoint. So when you look at a piece of software and you've used it before, but then you've talked to 5,000 other people that are using it every day, you suddenly get this breadth of understanding of kind of what's the intersection of the things that are the most important.
Yeah.
And it turns out that it's not 44-layer probe cards, right? I mean, I would love it to be,
right.
but it's not. The vast majority of products don't ship more than 50,000 pieces. The vast majority of circuit boards don't exceed 6 layers. The numbers of boards, certainly these days, this is kind of tipping in different directions depending on the technology that's sort of in fashion. But the majority of boards don't use blind and buried vias. It wasn't until kind of mid 2000s, late 2000s, I want to say 2007, 2008, that BGAs were approved for flight.
We're approved for flight. You mean like
flight,
like aeronautical stuff?
Yeah. So and that was in large part because the inspection was so difficult. And yes, we could do X-ray inspection, but the amount of contact for the material, making sure that all the pads really land where they should, and that there's enough strength in the bond between the individual balls and things like that. That was a fairly late thing to come on market, and we.
Well, it sounds like a trailing edge type of thing too, where there's like a lot of confidence. Not bleeding edge. It's not the. I forget what all the different names are, but it's like
but you're right.
Aerospace and like safety critical things are going to be trailing edge because they want
later
proof points, right?
Yeah.
Whereas
exactly.
an Apple or consumer goods in general would be willing to trade the size and the speed and the cost for reliability.
Yeah. And it's, it really comes down to yield. You hope that you don't get to market with something that fails. These days chips are so much easier to test to ensure the fact that you've got quality. And there's the other side of that, which is that we've just become far more of a consumer culture. So, if a customer has an expectation that every 2 years or 3 years they're going to replace their iPhone, how much do you care about the 10-year bond strength
vendor agreements and exactly.
It's all of that stuff kind of changes. I mean, obviously there are still industries like that have these very long lead times. Mm-hmm. I remember working with some guys on the emails project over at General Atomics, and General Atomics used to be a part of General Dynamics, but the emails project, which is public, it's not hidden away, is the aircraft launch system. So that magnetic aircraft launch system. So electromagnetic aircraft launch system is what EMAL stands for. And it was replacing the old steam slingshot.
Oh, this is on like carriers and stuff like that.
Yeah, and carriers and things like that. You want to put an F-16 or a F-18 up in the air. The slingshot, especially the steam-based ones, are incredibly harsh on the body of the aircraft, as are the arresters, right? You come in and, you're catching a plane that's coming in at, however many...
The impulse is high, right? Or the jerk is high.
Exactly. Exactly. But, if you think about it on a nuclear-powered aircraft carrier, electricity is not a problem, right? That's right. So, if you can leverage the nuclear reactor that you have, you can do some pretty interesting things. So they did some really, really interesting and exciting stuff. But I was talking with a guy and he said, we're building a system that is going on a ship that has a 50-year lifespan.
Oh, yeah.
The last rollout of this system will be on the ship that we build 50 years from today. So now think about that in terms of like just microprocessor,
right. And being able to buy it and sourcing.
Yeah. My source code has to run on a processor that's going to be around for 100 years.
Yeah. Oh my God.
Okay.
And there's likely, there's going to be upgrades and modifications, whatever, but still,
absolutely.
If not, you got to design for it, which is bonkers.
Right, right. So that's completely the flip side of consumer electronics, and it's interesting, the kind of dynamics there. But without getting too far off track, so meeting with the cross section of customers, you kind of find the intersection of what makes the most sense, and I think that really led me to want to contribute directly to the software and the product strategy that was going to help build the software that our customers needed. And that was, I don't shy away from the history that I had at Protel or at Altium. I think Protel, just for everybody's benefit, Protel eventually became Altium, and that was really a branding exercise. Right. That was because we had PCAD and we had Protel, and to sell two products within the same company at a similar price point to user bases that loved both meant that we were competing with ourselves internally. Somewhere was the intersection of both of those products. And it was really PCAD strengthened PCB at the time and Protel strengthened schematic. That eventually kind of became somewhat hybridized in Altium Designer, and Altium was the rebranding of the company. So,
and when did that happen? That was early 2000s.
Yeah, early 2000. So 2000, okay. 2001, something like that.
Okay.
So,
cool.
That I rode that wave for a long time, and then left and eventually joined Supplyframe. So left, started.
You skipped one step in there. You used to work with Dave.
I did. So I did work with Dave. Work with Dave in the same office.
I was trying to explain this to someone earlier that Matt's coming on the show, but the fact that you work on Eagle, now Fusion, right? Mm-hmm. And the fact that you worked with me and Dave, it's just these intersecting paths. It's just it's crazy.
Yeah, it is a weird kind of.
It's like a small industry.
Circuit,
that's what it comes down to.
Exactly. It's like when you go to Analog Aficionados, which if anybody has the benefit of going to, it's pretty cool. It's like the who's who of Silicon Valley analog ninjas.
That's right. And it's just coming up in early February. So they're. I think look that up.
It's such an amazing event. Yeah, if you haven't, if you haven't gotten a chance to go every year, it's kind of the who's who of the people that invented every analog device that just has moved the needle and moved the industry forward in huge ways. But it is, you realize how small the industry is. So I did work with Dave. And for whatever reason, I spent the majority of my adult life after electronics. And I shouldn't say after electronics, that's kind of misleading. I built electronics through that entire period, either directly or indirectly, working with customers, working with customers on behalf of the company, or working with customers outside of the company, and just building stuff, contracting to folks with just a whole variety of different things. Yeah. But I spent the majority of my adult life actually outside of the country. So I moved to Australia, spent better part of about 5 years in Australia, where Altium's corporate headquarters used to be in Sydney.
Yep.
And then eventually we relocated the corporate headquarters to Shanghai, and that was in part fueled by a couple of different forces. There were a few different things at play there. One of which was the obvious, hey, here is this burgeoning electronics market. They're graduating 500,000 electrical engineers every year. We have incredible market penetration, but not a lot of revenue. So what that translates to is we have an intellectual property problem, right? People are leveraging our software, using our software, and we need to be there on the ground if we want to have a credible opportunity to convert those customers
Start
from non-paid to paid.
Show value.
Just engage with people and say, hey, listen, we know that you've been knocking off the software, but you're a really big company, and we'd kind of like you to sign the guest book. So,
Right.
but then there's, the other side of that is that they were graduating, 500,000 engineers a year, and there's this huge opportunity in that space. Kind of happened right at the time in which Intel was throwing around, numbers of trillions of devices that were going to be connected via IoT, and it made a lot of sense.
Right, and we are
at least
getting there too. I think that was like the right number, but the wrong timing.
Yeah.
A consultant dropped like a date conversion or something like that.
Yeah, exactly. And it was. I think it was the right number. I think it was. It triggered unnatural acts to try to accelerate that, which I don't think were necessary.
Yeah.
I think we were going to get there anyway because every television was going to be connected to the internet. Every whiz bang thing around your house was eventually going to have internet connectivity. But the notion that connecting those things together was something that had to be exceedingly deliberate. I as much as I like my Amazon Echo, I don't know a lot of people that connect that to 100 different devices around their house.
That's right.
So I think we still haven't gotten to the aggregate intelligence, right? We've gotten to the sort of, it's connected to the internet. Great. It can stream some audio.
Right. That's pretty much what mine starts music for me and keeps kitchen timers. That's about the extent of it.
Mine too.
Yeah.
And
it does great at that though. I really like it, like from that perspective. I don't like the listening thing, but like the fact that it's just there and easy. Yeah. It plays music for my dog all day long. I also like that. It chills him out. He's listening to some Christmas jazz right now, Great stuff.
Yeah. And I think, it was somewhere in there. There was just the mistaken impression that somehow required us to all mobilize lots and lots of resources. And I think, there were lots of examples of startups, especially that were built, funded on the backs of, oh my gosh, IoT is coming. We're going to build something which is easy to add Wi-Fi to something. I don't think that that's altogether flawed. I mean, Espressif with the ESP8266 is pretty sweet. And having lived long enough, when there was a period there where we went from serial ports to USB, Rabbit Semiconductor, which these days I think are the guys that do a lot of Zigbee related stuff. Rabbit Semiconductor built these USB to serial converters. And they were plug and play modules. Now, on the backs of that, FTDI emerges, right? And you've got people who are building single chip USB to serial converters or serial to USB converters. And all of a sudden an industry like, we were talking earlier outside of the conversation about McDonald's, all those early POS systems that were used in the restaurant, the point of sale systems, they were all serial ports.
Yep.
And
exactly. Everything needs to be
required
updated.
amplification, and you got signal amplification because you're going to the back office. The back office might be, 20 meters away. Right. So, you've got a reasonable length of cable there. You've got signal amplification and attenuation issues. You've got all sorts of stuff, and people wanted to just plug into the back office computer.
The reference here is Matt used to work on some of these things as well in his Chicago days.
I know a little bit about it.
That's what he was saying. He said before, so I wanted to clear that up. Yeah. So so Matt was working on this stuff, and so you're saying that the connectivity piece was based in wires and physical things.
Wires and cables. Yeah. You get somebody out that would drag cable. And these days, I think, the translation of that, this sort of transition is toward wireless connectivity. And the expectation is wireless connectivity. Today, when you pull up to a drive-through.
I think there's still like a business need there too, right? It's not like they weren't doing it to be frivolous, right? McDonald's is a very good example of like, no, we have like thousands of locations. We need thousands of ways to quickly interact with customers. And now we can upgrade our systems and it doesn't have to be wired anymore. It's like, okay, we still have that need. Now it's just new technology layered on top of that.
Right. And I think it's the notion of that being something that was super deliberate. We all have to go out and somehow raise money and build businesses around that. I did that, right? So myself and the then CEO of Altium and I left Altium in 2012 and started a business in China, really focused on IoT with the goal of connecting infrastructure together. Because, here you're in this country that, in Shanghai alone today, there's 30 million people. right? Most populous city in the world.
It's just right.
30 million people.
Most states in the U.S. are less than that. So
exactly.
like
pausing
5
on that for a moment.
Yeah.
That is the population of Australia.
Oh yeah, there you go.
So
that's also good.
Yeah. So you concentrate that in one city. You've got this country that's going through the largest mass urbanization in history, meaning people are moving out of what were historically villages into cities, looking for not just a better quality of life, but looking to level up in terms of skill, capability, and contribute to the economy in a real way. And over there, I think that's a very real, from my experience over there, I'd spent better part of about 4 years there. That's a very real undercurrent that's underappreciated by people, is the interest in sort of mutual contribution to the economic growth and success of a country. It's very real and tangible kind of need for building out this technology, this functionality, these features that would connect together the infrastructure that's there. And that was in part informed by some experience that I had doing some early R&D for McDonald's. And that was that too was kind of an interesting project. It was, largely focused on the restaurant and how do you connect together the internals of a restaurant in a more intelligent way. And I, hats off to the guys at McDonald's. They were pioneers in this long before. I mean, the 900 megahertz Zigbee spec wasn't dry yet.
Yeah.
And they were asking questions like, how do we stop guys dragging cable through the restaurant?
Yeah, right.
Because to do that shuts down the restaurant, right?
Yeah.
How do we get all of our franchisees connected into a back office computer that connects to some larger back office infrastructure that eventually backs up into our corporate headquarters, so we can observe that somebody didn't just add 5-rolled tacos, rice and beans to the menu at McDonald's. It's really about discipline for them, and it's really about
and data. I mean, like that's an early focus on data as a resource and a not a commodity, but like a valuable thing.
Well, and they acknowledged, especially when they were trying to pull together McCafe.
Oh yeah.
I think rightly so. That. The ambient noise level in a restaurant at that time was just nuts. It was like going into a shopping mall. And you really need to bring that down if you want somebody to sit and have a cup of coffee. You need to bring that down if you want to compete with the Starbucks of the world. And I think everybody at that time was trying to figure out, what is this Starbucks thing, and what are the implications of this? How does this affect our business? What happens if they sell a sandwich, right? Yeah. So I think the stuff that we had endeavored to do in China was kind of the next generation of that thinking, at least for me, which was, how do you connect infrastructure together? So if every light on the highway from Los Angeles to Las Vegas is lit all day or all night, is that really necessary if the rate of trucks are, one every 60 seconds? And can we connect the lights together to follow the truck along that path? Can you look at then certain events and respond to them? A truck that is picked up by one sensor, but then immediately not picked up by another, such that you can sort of predict that something catastrophic happened in the period between here and here, because nothing slows down that fast. So, it was those kinds of interesting problems. I think I mentioned to you at one point the smoke detection stuff that I was very passionate about, which was, can you connect an HVAC system, which has some fluid dynamic simulation behind it, with the smoke sensor, with temperature sensing, with proximity detection. And it turns out that at the intersection of that are some really, really difficult problems of, as the temperature goes up, all of the electronics behave differently. As smoke starts to appear, what is a person in proximity to the proximity detector versus just smoke clouding the area. And as any good hacker knows, right, the dust spray that you use for your keyboard is an easy way to trip sensors that think that there's a human on the other side of it.
Yep.
But those sorts of problems become really, really interesting in that space. And I really wanted to solve a lot of those problems. Tragically, I don't feel like that chapter really ever closed for me. I feel like there's still an itch there that's got to be scratched at some point. And I
don't think sensors and or connectivity are going away anytime soon, Matt. So I think you got some time.
Yeah. So I got some time, right? I got some time.
Well, it's interesting too with the infrastructure idea too. Like you think about deployment timelines, right? We talked about the 50-year timeline of a ship, but when you think about like not only like getting things out in the world, or to use your example of sensors on the roads, right? Yeah, but maybe Phoenix is different than Tucson, is different than Flagstaff,
right.
and really what it takes is a bunch of churn and struggle, and then eventually some kind of general consensus of like, I guess we'll just all use this one thing, which still has not been decided. And so I think there's a lot of space for that still.
And I think
definitely churn.
There's definitely, and I think we still haven't decided what to do with the aggregate intelligence from all of those things.
Yeah, right. Usually,
because nobody's agreed
it goes
on
dystopian.
What that means.
Usually, Black Mirror picks up on it first.
We've still got a lot of work to do on that front. I was at an IoT conference and just as a panelist, and they'd asked us on the way out, hey, what do you think needs to change in the industry? And I said, I think we need to be exceedingly transparent in what data we're sending. And by that, what I mean is don't tell somebody that it's, your data is encrypted and it's coming via OpenSSL or something like that, or SSL. Let's be very, very different, and tell people we're going to collect this information. It's going to be sent to these people. So there's a level of accountability so I can make a choice. And I don't think that is unrealistic, but I think it's unrealistic, right? I think the commercial opportunity is just too great that unfortunately you don't get a lot of control over those things, in large part because the data is too valuable. So there's a lot of negative forces.
It's very pervasive. I think there's a lot of value in it, but I think that you're right. It's like it's a resource, and it's something that people should know what they're signing up for.
Yeah, absolutely. So anyway, fast forward, and I relocated back from China to the U.S. and decided to at that time I'd been spending a good deal of time hanging out with my good friends from SupplyFrame, who I'd started conversations with long before that at Altium, who has really focused very heavily around vertical search, targeting the electronics vertical, guys that were in part bootstrapped from the people that founded companies like Avnet and drove Marshall Electronics to eventually become one of the first online retailers of electronic parts. And it was just the story there was so interesting because there's so much in the supply chain around electronics that's poorly understood and taught nowhere. And having gone through the process of building commercial products and also higher volume consumer products, you realize that there is an art form in just how you capture things like attribute information, such that the person downstream who's on the receiving end of that can make decisions without too much constraint. And what SupplyFrame, I think, opened my eyes to was just how important and essential a part of the product design and manufacturing experience that was. And at the same time, SupplyFrame is just an amazing company to work at. I mean, you can attest to this. It's a fun place to work. They're super interesting and fun people.
Yeah, you get all the Hackaday stuff too. That's a lot of fun.
Yeah, exactly.
You and I and Sophie and Alec and a bunch of other people helped. That first SuperCon back 5 years ago. So it was a lot of fun.
Yeah, I remember my party planning days. That was, that was. But it was such a good time. It was such a good time, and it's. I look back on that with just incredible fondness because it when you when you want to be at that intersection, I think, of gathering data and intelligence and then leveraging that to do things like drive a better advertising experience, drive better access to content and resources, data sheets, reference designs, those sorts of things, drive better sort of pricing intelligence, exposing pricing from a bunch of different places and kind of aligning those things to one another. You really have to do right by the community. Otherwise, you're at risk of being viewed as the company that gathers lots and lots of data, and you're totally opaque to the user. And I think SupplyFrame really struck that right balance for me. Otherwise, I don't think, if it was like a LexisNexis, I always trip up on that. I don't know that I would have had the enthusiasm for something like that. But I also really like just trying to understand the big search problem. And they certainly went to extraordinary lengths to build out the infrastructure to handle some of those problems. So,
and I think, the data thing, like you said too, I think that's a good lead into the, Autodesk Eagle days. Like, a lot of the data that's being captured now for, on, more web connected tools like Fusion is, right? It's like you get more, you get value out of that because now you're tracking each and every move, and you're seeing that, and you have that networked, and there's also connectivity between different users as you want to do sharing tools and stuff like that.
Yeah, and I think there's, it's interesting. We talk about cloud data as though it's somehow this foreign body, and the truth is that people have been putting stuff in version control for quite a while, right? I mean, since the days of RCS, which is a revision control system, right? But nary an engineer doesn't have a GitHub account these days, and certainly your software engineers all have something in Git somewhere, or it's in Perforce, or it's in something else. But a lot of these are hosted solutions. A lot of that is the intellectual property that are, in fact, the keys to the castle. I think what we do with that data, and Autodesk, it's interesting because it's not really talked about outside of the company very much. But one of the things that comes up in conversation periodically is, what would we do with the data that we start to understand about customers? And the feedback is constantly, or the conversation amongst the executives, and I can only say this as a recipient of that, is we will only do those things that make sense to add value to that user.
Right.
So it's not about taking that data and in the aggregate somehow analyzing it and performing some set of things on top of that. The level of detail that we get is also not to the level in which it's actionable intelligence. In many cases, it's does somebody use the software? How frequently do they use the software? What parts of the software would you use? So
that is actually one thing that
building a better application experience.
Yeah, that's one thing that I learned from the SupplyFrame days is like just how spotty data is in general. Like not just what's out there and what's available, but also like you and I might both be searching for resistors, and we both want 49.9K resistors, but there's so few people searching for similar things at the same time that like correlating is really tough. And so I think what you're saying here is the data that you get around me as a user might be valuable to me, but it probably isn't as valuable to compare me to Bob down the road, to Jane, a couple of miles away from that, like it's more of a individualized experience.
Well, and I think and I think even more explicitly, it is wrong for us to triangulate user information in a way that is leveraged to try to drive user behavior, other than to drive user understanding and know-how and capability. So, for example, like in Fusion today, there's a workspace panel within the software that when you open an editor, knows that you opened, for example, like the CAM workspace. So, hey, this person cuts metal. Great.
Yeah.
You probably want to know how to use this. That in and of itself is built on your interactions, but it's targeting you, the individual, not targeting our our user base in general, right?
Mm-hmm. Yeah.
If there was something to be pulled out of that as like aggregate intelligence, then I think
Yeah.
we have an obligation to our users to be transparent about that and say, hey, do you want to explicitly opt in
Yeah.
to receive something which is going to take your information, collect it with a bunch of other information to give you the toolbar configured the way that most users leverage the most capabilities of the software. Like that would be an, kind of an obvious
Oh,
like
yeah,
double
I
click
see.
on that, right?
Sure. You're saying
So
like a float to the top kind of thing of like this is
yeah, yeah,
the
like a
most
bubble up
popular
kind of thing.
feature kind
Exactly.
of thing. Yeah, right. That makes sense.
Exactly. And I think, part of what I've tried to do in the Eagle UI, classically, it was just all over the map. And since we've integrated electronics capability into Fusion, is sort of look at the process as a workflow oriented process. So before, you had a toolbar and you kind of group things, kind of in lumps, right?
Mm-hmm.
You'd say like, okay, these are all the kind of line drawing related things, and
Yeah,
these are
yeah.
all the, this thing. But it's really about, how do I define a board outline? So, well, how do I set up my layers, define a board outline, place components, route them together, and pour my polygons, rip things up, and rework them.
Yep.
Right? Like if you just sort of put things on that continuum, then you can organize things in a way from left to right that are prioritized based on how most users would do things, and all of that is just coming from the experience that I've had in talking with, I don't know, God, over the course of the years, because I was in a tech sales team, I was a field apps guy, like, I spent, when you come up through a company which is relatively small at the time, I don't know, $30 million, growing that business over an extensive period of time. Today I think their market cap at Altium is what, 3.5 billion or something like that. So it's it's a substantial player now.
Yeah.
Where before we were the
Scrappers.
pirates, right? Yeah. We didn't have a right to play.
Yeah.
And we had to do a lot of work to ensure that we did get the right to play. So,
Right. So
when
a
you
lot of
look at something
listening to
like
customers and a lot of
listening to customers, going in
feedback.
there and, getting the pricing just right so that they could get it in with their approval.
Yeah.
Being
That's right.
sure that it was easy to install, easy to use, that it would run on just a desktop operating system.
Less than $5,000 goes on a credit card, and so it was priced at $49.99.
Exactly. Oh man, it was very deliberately priced at $49.99, and that was because we had that real sense of customer awareness. And there were lots of circumstances where people would say, "Hey, we just discovered that all of our engineers are using your product, even though we have these really expensive licenses of this or that." Can you tell us exactly who you are?
Right. Yeah.
And so, you sort of win by being scrappy by that. Well, almost invariably you win by being scrappy, but it's the willingness to be a little bit humble, acknowledge you maybe don't have the right to play today. Push the envelope in terms of technology, capability, functionality, and I, my hat's off to the guys over there. I think they've done a really good job of that. Mm-hmm. Even after my departure and the departure of a lot of the guys from the very, very early days of the company, continuing that push towards trying to build functionality and features that are relevant to the user. But you've got to do that quickly. You've got to do that in a very pragmatic way because you've got limited resources. And I think what we're doing today is actually kind of a reflection of that that experience, at least for me.
Yeah, so let's talk about that actually. So you mentioned, the Altium days was scrappy, had limited resources at the beginning, and now you're coming into Autodesk. Yeah. You have this new product. And then I think you have definitely the resources, but then maybe I'm curious actually of how much goodwill was there? Like, so like when you did decide maybe you wanted to move, the tool grouping or similar things or change some UI, what was the feedback like? Because it feels like Eagle has a very strong, loyal user base that are maybe resistant to change.
Well, so I think if there's one one reality that I came to grips with teaching workshops, teaching people how to design electronics, it was that people didn't use Eagle because of the ease of use in the UI until they got past a certain point.
Yeah. Sharp learning.
And it was,
I know this one well, man. I know this one well.
Well, and once you get beyond a certain threshold with Eagle, all of a sudden you realize what's good inside of it and why it was designed the way that it was. It took me a long time to figure out that, that for example, the layer names, you had names like T-Paste and
play on T-Pain, of course, right? It's T-Pain.
Yeah.
It's
but homage, T-Cream, B-Cream, and I'm it puzzled me for a long time. Why call this cream? It's solder paste. Come on, stop calling it cream. Here's the reality: software, Eagle is its native compilation environment was CentOS, and if anybody knows anything from the Nix days, Unix, Linux, whatever, the 2-character shortcut in Linux, Unix, whatnot, is the magic, right? So
ls,
sudo, right? So super user do, right? So the su being super user, giving you that leverage. Yeah. So ls, cd, you name it. So the layer names, because the command line in Eagle uses a starts with function, the layer names disambiguated, so that if you typed something, you only had to type the first 2 characters of it, and you would end up with the layer that you wanted. Now, that's magic for somebody that knows, but it is completely anathema to everything else that everybody else uses.
Right. Like, why is it called cream? This doesn't make any sense.
God, this doesn't make any sense. And then you're like, oh, well, there's no other TC in the list of layers. They picked something that would disambiguate. And that took me a really long time to understand. And some of those things I didn't find until I was in the source code.
Interesting.
And until we really brought the CADSoft guys in, or what were, the CADSoft guys into the organization, and kind of really tapped them on the shoulder and said, why this? So, in all of these applications, they're fundamentally very, very similar. You've got a command queue that handles commands from UI events. You've got a UI framework or a UI toolkit that builds the front end of that thing. And then you've got some underlying state machine that processes that. And you've got a data model for how you store that, both resident in memory and on a file system, right? So there, if I have to take the sum total of all of these experiences and kind of narrow them down to the very basics, that those are the very basics. So, if you're taking your computer engineering course and somebody's having you do state machines for the first time, rest assured, that is the rest of your life. So if you don't like it, I would bail now and go and start studying that, finally take that literature class that you've always liked. But being very serious about it though, that's kind of the fundamental application architecture. And when we looked at what the Eagle guys had in particular, the core of the application was very, very robust, very well written, extremely deliberate, very thoughtfully put together. And the user experience was something that the vast majority of new users really struggled with. Now, the legacy users, you have to imagine that in any software appliation,
well, especially a long living one. I think that's a key point too, right?
Yeah.
These days, apps live for 6 months? Hell, I couldn't install an app on a tablet that was a couple years old. A couple days ago.
Yeah, exactly. How many people are still playing Angry Birds, right?
Good
Bejeweled, or any of those things, right? Now, at one point, that was there's all sorts of fervor. I mean, they made a movie about it, for God's sake. So the reality is that you do have a long-standing user base, but over time, you lose those users in the renewal process, right? So especially with desktop software that is non-subscription, and I'm not going to shy away from that, you lose those users in the process. So you end up with a pretty substantial user base that just doesn't renew anymore.
Right. You're saying from a who you're then developing for is kind of that.
Yeah, exactly.
Whoever's
so
re-upping,
you're always
right?
developing for So you're always developing for a new base of users. over any period of time could, over a 5-year period, you would easily lose, 75% of your users. Now, testament to a good application is how sticky are they?
Right.
Are you
the ones who buy the next
by,
version, right?
Exactly.
Decide to go up.
Now, what changes with subscription a little bit, and I know that this is a controversial topic, but I'm not unwilling to chat about it. What changes with subscription is that the relationship is now one in which I have to constantly work to convince somebody, not every year, but every month, that it's worth spending more money with me.
Yeah.
And every month, some percentage of those people make a decision that they're going to renew. And I need to be there with answers to the things that are frustrating them and the things that make them unhappy, make them, uncomfortable. It's a bit like people who have their, $6 a month GitHub account so they can have more private repos, or I don't know if it's still $6, but it was $6.
It's actually free now. But yeah,
is it?
Yeah. Thanks. Microsoft.
Viva Microsoft.
Yeah. Right.
Yeah, thanks. It's those accounts that you're paying something on a regular basis. It creates a predictable stream of revenue, which I think is really important. There were too many years where it was feast or famine. Because the amount of software engineering that you're putting into these things to solve some of these big problems, these are long lead time problems. Some of them are really, really hard to solve.
Yeah, structural stuff that will propagate.
Foundational stuff.
Yeah, right. You
decide
to rewire something, and it's just like, oh my god, everything touches that one piece of the graphic thing.
Yeah, exactly. So probably the best case in point was the move to DirectX. At Altium, which paved the way for 3D visualization, and the move away from OpenGL, GDI type rendering to DirectX, and that was because DirectX 9 was the first to introduce instancing, and instancing. If you don't know, instance variables are a way to represent a single variable in memory and then instance it all over the place. Inside of the graphics pipeline, and that reduces the memory footprint and a lot of the computational overhead. So anyway, the point is that you make a foundational change like that. 2 years later, you deliver something like 3D visualization, and users say, oh, well, now we understand why you did it. But before we hate you. And those are long lead time problems. In some cases, you're going to break things. You're going to go back in terms of capability. But you've got to have a sense of humor about that. And or if nothing else, you got to have a thick skin, right? Yeah. And I think the more that you're transparent with your users and you say, hey, we're doing this, but this is what we're aspiring to do, the better. Right.
Yeah, so, that's a tough balance to strike too, because I think a lot of businesses aren't prepared to say we're going here because they either don't want their competitors to see it or they don't know if it's going to work, and so that's tough when you aren't able to say, hey, we're going towards this thing in the future. Like I don't think you were allowed to say we're moving towards fusion electronics. But
right, and we very deliberately held off on that, and in part because there's also competing financial pressures, right?
Sure, of course. You want to keep it. People keep paying. It's the cannibalization problem, right?
Yeah, well, and it's also just a revenue problem, right? Like if people are buying because you've given them a fixed timeline for when something is going to happen, and then you don't deliver.
Oh, sure.
Then can you really recognize that revenue as tied to the product that you had at that point in time? So we've been very, very hesitant to say anything related to when this is coming out, and I won't say that because there's.
Oh, we're not getting a date today. I didn't realize that.
No. Sorry.
That's right.
Yeah, but it's the fact that I'm showing it to you on screen gives you kind of an indication of where we're at. There's still, quite a bit of work to be done between now and the time at which we release things. But there's some really interesting things that I think over the lifespan of a career were things that I kind of always hoped we would achieve, but were just impossible. And, if you think about mechanical design and manufacturing as being the core competency, certainly of my division at Autodesk. And Autodesk owns Maya and Max, the media and entertainment division, totally different. And then, AutoCAD and Revit and BIM 360, these big architecture, engineering, construction division. I live in the manufacturing division. And in the manufacturing division, we focus on product design and manufacturing, right? So Inventor is one example of that, Fusion 360, mechanical design and manufacturing, but it's, cutting metal, 3D printing, injection molding with mold flow, it's nesting, sheet metal nesting, all of these sorts of things. So when you look at an industry like mechanical design and manufacturing, it's really only a couple of adjacencies, other industries that make sense adjacent to that. One of which would be, PDM, PLM, and that's why I think a lot of the mechanical design companies have their own respective solutions. Fusion has Fusion Lifecycle, which is lifecycle management, and super powerful lifecycle management that can store the state of a design as it moves through the pipeline. Right. And then on the other side of that is really electronics, because there isn't a circuit board that doesn't get put into an enclosure. And if every enclosure was a DIN rail case, all the electrical engineers in the world would be happy.
Yes, I would be. And
nobody else would pull the blister pack off of the shelf. I'm like, right. God, that's so pragmatic. Finally, a place for me to put all of my electronics.
If we could just get like a DIN rail that attaches to your wrist, then we could finally make a good watch.
Exactly. Hey, what is a Pip Boy except for a DIN rail on your wrist?
That's right.
So the key here was, we didn't want to just stick electronics design into Fusion. So a few things that were kind of table stakes for what we wanted to do. The mechanical world has things like thermal simulation, things like stress analysis, really good tools for grabbing a face and saying, generate a geometry from that or project a sketch from that. The mechanical world has things which are totally missing in the PCB world, like spline curves.
Oh, yeah.
And so I'm proud to say, at least as far as I know, and so that's a pretty horrible qualifier, but that we've added spline curves for board shape definitions. And so that way we can now align to what the mechanical engineer is doing. So it isn't this piecewise approximation of a curve that's within marginal tolerances of what was going to show up on the mechanical side, but that those two things represent the same piece of data.
Yeah.
Moving back and forth.
So let's do a little bit of structural stuff here, though, too. So
sure.
So Fusion Electronics, is that what it's called? Is that the title?
Or it's just Fusion 360.
Fusion 360, but the electronics portion of Fusion 360.
Yep.
This is now so diverging from Eagle. Is that right?
Yeah. So
maybe dovetailing again later, but as of right now,
I don't think we have to. So we don't have to kill Desktop Eagle.
Sure,
and we have no intent to do that.
Of course.
What people know and like about Desktop Eagle as something that's just simple, easy to use, kind of hanging out on the desktop, like that doesn't go away. But on the other side of that is the sort of holistic electromechanical design and manufacturing. Bolting on to mechanical design and manufacturing, the electromechanical side of that. That's really that's the evolution of it.
Yeah. Well, I think about so there was a converter at one point that exists right now, rather, that allows you to go between Eagle and Fusion 360, and that was a cool development. But that is basically a database transformation. As I saw it, it was like a click a button, things update, things calculate in the back end, and then you have the update over on one. That is no longer the case. Now it's basically you're in mechanical, you're working on electronics. Everything is just the videos I've seen from the demo was seamless.
Yeah, and there are a few fundamental things which are important to understand, and I'll share with you because I'm sharing my screen with Chris, but I'll share with you by my screen. But then I'm also going to explain them as I do them. Fundamentally, the major shift in mechanical design in the last 20 years has been parametric editing, parametric modeling.
Yeah.
So everything exists on a timeline. There's a continuum. Everything downstream is calculated by events that occur upstream. And so, if I create a sketch and I modify something inside of a sketch and I draw, some body I draw a circle or something like that. I grab the sketch. I say, okay, my sketch is done. I choose to extrude something. I extrude something by some height. I then shell something.
Right. And
now
actually,
I've got
to take it back
enclosure.
to what we were talking about earlier, this is like the Tinkercad thing. This is the recipe you had mentioned with Tinkercad is draw a thing, pull a thing, but these actions can be replicated arbitrarily in any software effectively, right?
Exactly. And now, if I take something like what I've got on screen here, and I've got, a timeline showing up, the origin sketch for something that I extruded and shelled can be edited. And in just editing that sketch and changing whatever that sketch is, I can recalculate certain things downstream. So I can take something else and merge two sketch bodies together with one another and merge that thing into one thing and extrude it and create something new. The challenge historically with ECAD MCAD synchronization was that you would pass a static model, what we would sort of in the mechanical world refer to as a direct model, right? Something that doesn't have history, something that's non-parametric.
Right. It's almost a mesh. Effectively, right? Like you're saying.
Exactly. Really. It's a relatively unintelligent sort of thing. So you would grab a static model from somebody, and you would say, okay, I'm going to bring this into the system, and then I'm going to build an enclosure around it. Or somebody would build an enclosure and send you a DXF, right? So STEP, IDF, any of those interexchange formats, they are sort of predicated on the notion that I send you a geometry and you use the geometry. But the mechanical world, there is this real implication, which is that I have a timeline, and that timeline is fed by that geometric information such that the downstream calculation of whatever that thing is, it needs to be considered in the overall analysis. So what we did with the Eagle to Fusion was we insert the PCB into the timeline. Okay. So we create a sketch, and then we insert that sketch into the timeline, and then we extrude that sketch to create the board shape. And then from there, that board shape could be projected.
This is the current conversion, or this is
that's a current conversion. So that's a current sort of Eagle to Fusion.
Got it.
So we insert that sketch into a timeline, we create a PCB, we place a component. So fundamentally, ECAD MCAD synchronization, the two things historically that we cared about were board shape and component position.
That's right. Yeah. Okay.
Now I would argue that that's a way too limited view of the problem, but I can demonstrate why that makes sense. Why what I'm suggesting actually makes sense. So, I can take now in Fusion, in the current implementation, and go the other direction, say I have a geometry. And from the geometry, like an extruded enclosure or something like that, I can grab a face, project something, and produce a sketch from some geometry somewhere. And on the basis of that, I can create a PCB. And now the geometry and the PCB are linked to one another in a way in which I have a PCB board shape that now matches the geometry that was used to create the enclosure. So all of a sudden then I have a PCB which now is linked to some underlying geometry through associativity. So if the PCB board shape changes, so I go from a 3D board to a 2D board, I generate a 2D PCB from the 3D PCB, and I start to manipulate the 2D board shape. I can cascade that change then back through to the 3D PCB, and those things just work forward and backward, however I want those things to work. And that level of associativity and timeline sensitivity means that the joints that people create, the projections that they create, aren't broken as a part of that process. That's hugely expensive for the mechanical engineer. Yeah. Sending them a new step model means all the downstream joints need to be reassociated. You've got all of this work that you've got to do. It could be hours of work, depending on the nature of the design. So what we've done within the Fusion environment is kind of take it a step further and say, can I take any geometry anywhere? It doesn't matter what it is, and project a sketch from it. And then from that, can I associate that sketch with a circuit board? And then from that, can I generate that enclosure from that circuit board geometry? And the answer is yes. Like we can manage both of those things in a pretty clean, pretty tidy way.
So is the assumption that the changes will be often enough that will impact this kind of back and forth? Because I definitely agree that there's stress at the point of transition, right? So I've handed off designs to mechanical as a step file. Mm-hmm. They've handed me back a DXF and say, no, the hole should be here. You'd redo this. Usually it's at the beginning, but any time there's a transition of knowledge or data like this, it is a stressful thing, right? So is the assumption that this is going to happen more often in this scenario?
So I think the assumption is that it can happen more often. I would hesitate to say that it will. I think we are more deliberate today because of the lack of frequency in terms of, or the price of frequency rather. So, I make lots and lots of commits to a Git repo before I submit a pull request.
Right. Yep.
And I do that because I have the flexibility of committing something to somewhere other than my machine.
Right. Well, and also because the cost of the integration is high, right? Like whoever's doing the request merging, that's their time, and you want to respect that.
Correct. And incrementally, people can grab my branch and they can test individual things. And, I can give something to QA long before it's done, air quotes around done, but long before it's like truly complete and merged into the software, and say, hey, just follow this branch over here. Oh, you didn't find, I left the via button out of the toolbar or something like that. Okay, cool. I added it back here. Just pull this. And it gives us that sort of frequency in which we can interact as an organization. It's not exclusively the mechanical engineer, electrical engineer. It's kind of every other stakeholder in the process. So, some of the capabilities within Fusion, like the T-Splines workspace, that's a mesh editor. And T-Splines was integrated into Fusion years back. That's a mesh editor for industrial design largely. So it's all of the complex contours and forms and sweeps and, all the sorts of things that make a product look amazing. Get somebody to say, mommy, give me one of those and grab a blister pack, right?
Yeah. So this is the one where you can actually like grab, it's like you're basically like molding in Fusion, you're saying, or whatever that
exactly.
That menu is.
Exactly. It's like kind of that sculpting style approach to things.
Sculpting, that's it. Okay.
And that's necessary for really good consumer products, really good industrial design. Now, the mesh to BREP conversion is, okay, how do I make that then useful in the mechanical world too? Right. So, in the mechanical world, I want solid bodies. I want to know that I can grab that edge and chamfer it. If it's a bunch of triangles, is that an edge?
Right. I want to mill it out with something.
A lot of computation. Yeah, exactly.
Yeah.
So, some of the things which have been really essential, at least from my vantage point, some of the things that I felt were really essential were that if we were going to do the 3D PCB capabilities in Fusion, that we didn't shirk on our responsibility to do things like question whether or not a board could be fully extruded, meaning that the copper could be extruded, the solder mask could be extruded, that I could have a positive extrusion for the copper along the z-axis and then a negative for the solder mask, that I could have real solid body geometry. And there's a meaningful reason for that. When you go into something like thermal analysis, the thermal analysis tools, whatever it is, are going to mesh it for thermal analysis, right? It's FEA, right? So they've got to triangulate that in a way that computationally works for thermal analysis.
Yeah.
The CAM tools, the milling tools that would do something like allow you to cut a prototype on an LPKF or a Roland or another mill or any of those things, those tools also will generally mesh the model when you go through the process. They mesh things slightly differently, and it's opportunistic. If I want to 3D print something, it's much easier to start with a solid body and then bring it into the 3D print environment and print it so that I can do things like a test fit for connectors or make sure that the holes are in the right location and that, my M3 screws are going to fit through that. I had the tolerance a little tight. I don't know that that's really going to work. So what we did, which I think is really the more kind of revolutionary side of things, is we figured out how to do it all as solid body.
And so can you contrast that Can you contrast that to how that's done now, though? Like, so solid body versus blank
versus mesh. So
Okay.
probably
Okay.
an example. One example would be that that kind of, and this is kind of a more philosophical analogy, I guess. One example would be sort of the difference between looking at a picture of the Grand Canyon and standing at the Grand Canyon, right? Looking over and actually seeing something. You've got this level of fidelity in the geometry. That means that when I highlight something, it doesn't just exist on the graphics card. It doesn't just exist in the render pipeline. It's a real geometry that can take a material and have the material applied to it. And it has this cascade of implications, like I can mesh it for electronics cooling or thermal simulation. I can mesh it for.
So real quick on that then.
Yeah.
So the idea would be if I'm drawing a trace now, it's effectively like I'm drawing a tiny square or rectangle, and then I'm extruding that along the path that I'm dragging with my cursor as a trace.
Yeah, so that's pretty much it. The key is I still want to keep PCB routing in the 2D domain, at least for now. I think there's all sorts of questions about whether or not we could go another direction with that. So, and this one didn't have the bodies loaded, but what you see here are kind of the breakdown of things. So if I sort of remove the solder mask on a board, and I'm showing Chris this is the beagle bone. If I remove the solder mask on this, you can see like all of the copper geometry now can be highlighted. It's not just sitting on the render. It's not just sitting on the renderer. There's real hit tests. I can really follow tracks in three-dimensional space. I can highlight individual signals and kind of follow them through the pipeline. I can see the individual signals that connect to individual component pads, and I can follow from component pads the entire net through a board. Now, just doing that was historically very, very difficult to do. Computationally way too intensive, and so in large part people punt on this. But we figured out how to do it, and to do that in a way that's performant, where the copper is actually extruded, where it has real geometry to it, and then can immediately come into the thermal simulation environment with the properties of metal.
And it looks So to give a word picture for people here, Matt's showing me copper with a bunch of vias in it, and the vias are connected thermally to a ground pour there, but then I can see the segments that are drawing, like when you see that kind of bullseye looking thing around a via, when it's connected thermally, I see the actual circular segments around the edge, which it looks like is crafted versus, however that would be done otherwise.
Yeah. And so, in a mesh modeler, you get some high performance out of it because it's really existing in the rendering pipeline. In this case, we're treating this as real copper geometry, and as a result, we can apply materials to it. And if I can apply a real materials definition, and I don't mean an appearance, there's a distinction there, which is important because materials have reflective properties and all sorts of thermal characteristics, and
not just graphical stuff either, right? I mean, you have
exactly, and then to hit that with 30 frames a second tumbling. Spin in a view cube somewhere, and you lose a lot of this fidelity when you look at something over Zoom or something like that.
Right.
But to hit 30 frames a second or 40 frames a second or 60 frames a second or whatever, it's non-trivial. But that solid body copper means that we're introducing potentially tens of thousands of edges, and we still have the level of performance that has never been done before.
The edges, can you explain the edges piece? So the edges...
Yeah, so the edges are the actual edges of the solid body. So, if you think about each thing having an edge, in a triangulated mesh, everything is triangulated. There is no edge. It's just triangles. The triangles have their own respective edges, but there is no shared edge across those things because it's been meshed.
So this is just math in a processor, math in a GPU kind of problem?
Correct. But a really sophisticated kind of problem about where do you put it in the nodes in the tree and so on and so forth. Then, doing the equivalent with the solder mask to say, okay, now I'm going to do a negative extrude of the solder mask on top of that, compounds the problem, right? Now you've got twice the geometry. And then to layer components into that and still have it be performant. And then doing that with a pipeline that is still parametric is a hugely complex computational problem, but we nailed it. we
Right.
achieved it.
That's great. Can you speak a little bit about the benefits of what will come after this? So like thermal
Yes.
simulations
Yeah.
and
So thermal
like high speed
simulation is one
simulations.
that, yeah. So thermal simulation is one that jumps out as the most obvious in the short term because Fusion already has thermal simulation. So my ideal case for thermal simulation, we're still a little ways from this, but my ideal case for thermal simulation would be you drop a QFN on top of the board and you put your vias underneath that QFN, faithfully hoping that you're going to wick away the heat
Mm-hmm.
from that device and transfer it to the opposite side of the board. In that case, how do you know whether you have the right number of vias, right?
Oh, sure.
Is that the right combination, the right position? If you follow the data sheet, you hope that that's accurate. But did
Right.
the data sheet tell you that they used 1 ounce copper, half ounce copper, 2 ounce copper? Maybe they did, maybe they didn't.
Yeah. Did they simulate it? Did they actually just do
did
it
they simulate
empirically?
it?
That
Did
kind
they
of thing.
just,
Right.
yeah, exactly. Hey, we did it and it's not catching fire.
Right.
So every customer who wants to build a consumer product, for example, is going to go through underwriters.
Yep.
Part of that effort going through underwriters is going to be that you need to account for those scenarios. Let's say I'm building a baby monitor, right? Wireless baby monitor is probably one of the more disastrous things for anybody to endeavor to build because you've got FCC certification, CE certification, underwriters, you've got all sorts of stuff there. Then you've got the security problem of you're transferring video over of your baby over a wireless connection. So you've got the security issue. There's just a whole bunch of problems with that. So, do you know that it's going to be 50 degrees C on the surface? So what this paves the way for, and this is, I don't want to sell snake oil futures, but what it paves the way for is being able to look at some of those problems and then evaluate them in the totality of the enclosure to say the temperature rise of this part will drive this property above this threshold such that the material itself that represents the enclosure, whether it's ABS plastic being injection molded or whatnot, will transfer this much heat to the other side of that. And that means that the surface temperature of this at this point is X. That's almost the holy grail. The real holy grail is that at some point you feed that into a pipeline that can then say, okay, well, what happens if I move it over here? And what happens if I move it over here? And what happens if I move it over here? And so, some of the
do like generative kind of stuff too. Then,
so some of the stuff that we've been playing around with, and there's quite a bit kind of in flight right now. But some of the stuff that we've been playing around with are things like, we added the quick route capability to Eagle a couple of years ago, and that's sort of like one click, one kill, route something. If I decided at some point that I wanted to, rip up and reroute a part, the one click, one kill of the quick route capabilities is not intended to be your all singing, all dancing auto router. What instead it's intended to do is say, hey, I've got some connection from here to here. Just solve that for me. And it can do diff pairs and it can do length tuning and it can do a variety of different things. So, but that was really paving the way for a reroute command to say, you know what, I want you to, and if I can remember how to spell it, so it's reroute device, and it would go in and recalculate the connections on a given device on the board. And this is a fairly sophisticated board to try to solve that problem for, but it would go in and try to rip up and reroute the connections. That would connect through. So you can see it made some changes to the actual connections of U2 here. If I sort of undo those changes, you'll see that, it actually rerouted those. So the reason to do that was that now the move command in the mechanical world, which can be used to move connectors, which is largely what the mechanical engineer is going to move a connector around, can have an option to automatically rip up and reroute the connection on the PCB side, on the 2D PCB side. And that paves the way for us to have some really, really interesting workflows that then eventually tie into the generative stuff. Now move this part, okay, and based on that, I want you to rip up and reroute this one or rip up and reroute that one based on the changes that I'm making to these individual things. And it that's when it starts to get really, really exciting. So what we've done is managed to kind of paved the way for all.
Yeah, that was the demo video that I saw for that you just shown off at the Australia conference you guys had.
Yeah. So, there's a whole variety of those sorts of things that are in the works and being kind of, thought through in a very, I opened up a blank PCB, being thought through in a very kind of intelligent and, hopefully intelligent. I'll let history be the judge, but being thought through in a way that has a real awareness of the overall pipeline.
So this is actually really, this is great. This is great stuff. And it seems like you're looking for feedback on all this. Where can people find out more, maybe watch that video, the demo video, and then see more about this and get in contact?
Yeah. So you can follow me on Twitter. It's Technolomaniac. We can throw it in show notes or whatnot.
Yep,
but
definitely.
I've been, they say the ship leaks from the top, right? So, I've been leaking out information on a pretty regular basis. But you can follow me there. There'll be a bunch of stuff. You can also see the Autodesk Eagle and the Autodesk Fusion 360 Twitter feeds, composing a bunch of videos now, and I'll share, a bunch of that content and get a lot of that stuff out there.
Okay, great.
And then, as we get closer to the release, we'll definitely let people know and try to bring in a community of people to really test things out and help us to make the right decisions prior to putting this all out there.
Awesome. Well, this has been a whirlwind through, EDA and, I really do. I mean, I'm sorry I'm not switching over from KiCad anytime soon, but I am a Fusion 360 user. I love the software. I think it's been making lots of great strides. And I think all of this stuff is a really, interesting seeing where things are going. It's very
I appreciate
interesting.
it, man. It's a bit of a magnum opus, so we'll see how things go. I don't want to drop the mic and walk off stage. I think what we've done right now is really race, to sort of mix metaphors. We've raced to the start line, so we're at the starting line now.
Yeah,
and
it's a new paradigm.
Our battle to win.
Yeah, exactly. And I think that you're gonna, it's gonna be a little bit of a struggle to get people to try new things. But even Fusion was a new way of getting people to do mechanical CAD. I think that there's a lot to be gained from kind of meshing of the software and mechanical and electrical worlds. And I think there's going to be a lot of interesting things there.
Yeah, I agree.
Well, I'm glad you have been doing a lot of cool stuff, Matt, and keep up the good work. And
thanks, man. Thanks. I really appreciate it, and thanks for having me on. It's great,
thanks for joining us.
Chatting with you. All right, thank you. All right, take care.